we will look at macroscopic particles. So today would be the last day when we talk about the different modes in which we collect information about astronomical objects to study our universe. And particularly some of you come from a geology background, and where I slip, because you probably know far more about rocks than I do, do chip in and give your interpretation or give your inputs. That would be much appreciated. So we'll talk about meteorites, we'll talk a little bit about lunar samples, and we'll talk of dust. So far you've seen that the bulk of the information, and that is true, has come from the electromagnetic radiation. We also talked about cosmic ray particles, and we talked about neutrinos. So today is a day for, at least the first part, for our understanding of macroscopic particles in the universe. And today we are meeting on Gandhi Jayanti, so I thought I should just remind you all that these are pictures of Gandhi, some of our freedom fighters at that time, Maulana Azad, Jamnalal Bajaj, Vallabhbhai Patel, Subhash Bose, and this is Mahadev Desai, who was a long-time associate of Gandhi, and a lot of what Gandhi did. The credit should also go to Mahadev Desai. Probably it has not gone as much as Ramchandra Guha recently pointed out in one of his articles. And when they were all lodged in prison, actually, apparently Mahadev Desai studied French, Vallabhbhai Sanskrit, and Gandhi actually spent some time studying astronomy. And this was I picked up from a book by Rajmohan Gandhi on Patel Alive. And he said that the stars address silent discourses to us is what Mahatma mused, and it is holy companionship. So as remembering Gandhi, I mean, all of you, must work towards being good academics, but you must also work towards being, great human beings, compassionate, and with empathy and kindness towards all, and get away from any kinds of discrimination, either in the basis of gender, religion, etc. Teach all, reach out and teach all, reach out to all with kindness, sympathy, and empathy. Okay. So before we start the lessons on meteorites, after these opening remarks, can I ask you how many of you recognize these two pictures? You can unmute and say.
So the one on the left is this lake, right? I don't recall its name. Somewhere.
Lunar Lake.
Yes, that's the one.
That's the one. Very good. And who said Lunar?
Me, Mansi.
Mansi. Okay, excellent. Okay, and the one on the right?
The one on the right, is that the Arizona crater?
Excellent, Ahan. Yeah, excellent. Both Ahan and Mansi. Okay. Somesh comes from Buldana. Somesh, you have been there, or are you there today?
Yes, I have been there. Like actually, it's near from my hometown where I live. It's quite not that far.
Not that far, right? Okay, excellent. So this is Lonar Lake on the left, which is in Buldana district of Maharashtra, and this is due to a meteorite impact over about 50,000 years ago. The rim diameter is about 1.8 kilometers or so. And this has also been declared a Ramsar site. And a Ramsar site, this is based on a treaty which was signed in a place called Ramsar, I think it's Iran. And this gives special protections or special recognition to wetland areas, which are of interest for conservation of water birds. So there are not too many sites in the country, but Lonar Lake is one of them. And the right one, as you all mentioned, is a meteor crater in Arizona. And this is also roughly about 50,000 years ago. And the diameter is about 1.2 kilometers. The geography is very different. You can see this was, once it was more green than what it is now many, many years ago, but it is almost desert-like over there. And they have set up a nice visitor center. You can walk up and go around the rim a little bit. And this property is actually privately owned, so it is not really federal or US government property. And the word meteor over here actually comes from the nearest post office. It is, they, in the US, they can name they can name these sites after the nearest post office, and that's how it got its name from, meteor crater. So these are the results of large impacts. Okay, these are really large impacts, and these create these craters on the Earth. There are not too many of them, fortunately, and it doesn't happen too frequently, as we shall see in a short while, but these are at a high end. Let us look at a smaller range. Okay? We get inundated by particles, actually. We are not, the Earth gets hit by small meteoritic particles, and some of them are very small. If you take the range of about 10 to the power of -5 to about 100 milligrams or so, the largest contribution is about, they descend upon the Earth each year, and the total mass which is estimated is about 2 million kilograms of meteoritic particles which descend on the Earth. This is what one is only talking about, the smaller sized ones. And these are basically swept up interplanetary debris as the Earth moves around the sun, typically from asteroids, comets, etc. So the mass range is actually much wider than what I have written over here, 10 to the power of -5 to 100 milligrams. You can get them in much smaller as well as larger masses. And we shall see that the kind of meteorites which created these craters at both Lunar as well as at Arizona were much, much larger. Okay, so you can see that that meteoritic particles or meteorites is something which is quite common. And the most smallest ones, they don't even descend on the Earth, they will burn up in the atmosphere. And the slightly bigger ones will survive and hit the Earth. Now, meteoroid, just recap on the terminology which is often used, but people also use this interchangeably. So meteoroid is any rocky material before and during its passage through the Earth's atmosphere. And a meteor is the optical and related phenomena as a meteoroid travels through the atmosphere. But as I said, people often use this interchangeably, but you would often hear the phrase meteor shower, for example, at particular times of the year when the Earth passes through a region where there's an increased density of this interplanetary dust or material, and you get these meteor showers. A meteorite is any rocky material that has reached the Earth. That is what you collect or receive on the Earth. And as these particles or masses, rocky bodies go through the atmosphere, they burn up. The huge meteors actually, they may fragment and not fall onto the Earth as one piece. And the bright and the very bright meteors are called fireballs and bonites. But again, these terms are used interchangeably. But all you should remember is that when we are talking about a fireball or a bonite, you're effectively talking about a rock from interstellar space burning up in our atmosphere. Now, we talked about the small ones just now, and I alluded to that, the fact that they can be much more massive. So how much more massive and how frequently does it come? Now, we'll spend a minute or two on this graph. Now, this is a model dependent because they reconstruct it from what they observe. And what is shown over here is the energy, the bolide energy in kilotons of TNT. So 1 kiloton of TNT is about 4.2 into 10 to the power of 12 joules. Okay. Just to give you the scale, the kind of energies we are talking about, for example, the atomic bomb, which was very tragically dropped at Nagasaki, was about 20 kilotons of TNT. Okay. Now you can see over here when you look at the top, which gives you the mass in kilograms, okay? Mass in kilograms. This is from 0.01 kilograms to about 10 to the power of 9 kilograms is what's been plotted over here. On the upper scale, which you can see is kilograms. And on the lower scale, what you can see is the diameter in meters. Okay? So you can see that it goes from a small fraction of a meter to about 100 meters or so. And like a lot of things in the natural world, there are far more of the smaller variety, small in mass, small in size, and as you go to large masses, they become less and less frequent. And this is in orders of magnitude. This is also in orders of magnitude. So this curve over here, this line, this power law, can be described roughly as the number is equal to 3.7 into e to the power of -0.9. So different people have arrived at slightly different ranges over here. So this is just a ballpark number. Now you want to sort of get an idea of how often do we get hit by these meteorites. So if you take about 40 centimeters, say, okay, greater than about 40 centimeters over here, so 40 would be somewhere over here. So you can see that there are roughly, this is 100, this is 1,000. So it'll be about 500 impacts per year, okay? With 500 impacts per year with mass of the order of slightly greater than 100 kilograms and a size limit of about 40 centimeters. Now, if you go to the highest ranges, okay, for example, 10 to the power of 8 kilograms or so, then you find that it is about 10 to the power of -3, -4 kind of thing. So if you want to talk about 100 million kilograms, which as you can see is about 40 meters in diameter. So you'd have seen a 100-meter race, so you know what 100-meter looks like. And this is slightly less than half of that. So it's a pretty huge chunk of rock. But that happens only in about once in 1,000 to 10,000 years in this particular range. So you can see that the more massive impacts are very infrequent. Whereas when you go to lower masses, they happen quite frequently. Okay? And just to make a note of the masses that we're talking about. But in addition to the mass range that I've shown over here, we saw earlier that there are small particles of interplanetary dust which gets swept up continuously throughout the year. But as I mentioned, that is about 1 million kilograms or so. But again, if you compare this with the mass of the Earth, it's a tiny, tiny, tiny minuscule. So we don't need to worry too much, but it is a very, very, very small fraction. But in terms of the actual mass, it is quite a significant quantity. The fireballs, the glows which one observes, are produced by meteorites, which are meter to decimeter size ones. And when you have large sizes, as I mentioned, they will detonate in the atmosphere, and it'll fragment in the atmosphere, and smaller particles, smaller sizes could reach the Earth. A 50-meter diameter is about 10,000 kilotons of TNT. And as I mentioned a bit while earlier, just to remind you again, 1 kiloton is about 4.2 into 10 to the power of 12 joules. So these events don't occur very frequently, but they do occur. And one of the well-documented events was an event in Siberia, the Tunguska event in 1908, which actually flattened about 2,000 square kilometers of forests. And larger objects than these would produce craters, and these craters are larger than the rocks. And the more energies that are there in these rocks that hit the ground, the greater is the diameter of it. So this is again an approximate scaling relationship which has been sort of arrived at from the known craters that we have. Now, where do these particles come from?
Sir.
Go ahead.
Sir, in the previous slide, in the graph, what does the discontinuous line represent?
What does
these discontinuous lines on the split?
Actually, these ones, I think this is what is from the Earth. I think these are estimates from the lunar craters. And most of the meteorites actually come from the asteroid belt. And asteroid belt, we'll have a look at it a bit more detail when you look at the solar system, but it's a belt between Mars and Jupiter. It is probably a region where a planet would have formed, but due to perturbations or disturbances from Jupiter, it didn't quite coagulate to form a planet. So there were a lot of these planetesimals which probably broke up into rocks. It didn't really aggregate to form a planet, but you have a whole lot of rocky material over here. And these could be disturbed by various processes, including by Jupiter, so that some of them stray out from their orbits and bombard other parts of the planetary system. The asteroids, as well as the sun itself and the planets, are believed to have formed from a pre-solar nebula. As when we look at star formation in a bit more detail, we'll look at how this goes about. The mass will have to be greater than a certain mass for stars to form. And people have done pretty detailed calculations of how things would evolve from thermodynamic calculations of a very hot pre-solar nebula to condense into the sun at the center and the planetary system as we know it today. But the origin would be a star formation region in a giant molecular cloud. Now, when these condensations took place, one of the important sort of clues has been from studies of what are called chondrite meteorites, which are basically rocky meteorites, and they have what are called the calcium aluminum inclusions. And these are what are these white specks over here, which would have condensed and formed these spherical globules, which are sub-millimeter to centimeter sized, and they are found within these chondritic meteorites. So chondrites are stony type meteorites containing these chondrules. And these are among the oldest rocky bodies. Dating these effectively determines the age of the solar system. So this is one way of trying to determine how old not only the Earth is, but how old the whole planetary system is by looking at these meteorites. So these provide us an important clue towards dating the solar system. Now, how old do you think the Earth is, and how would you estimate it? So any sort of comments on how old do you all think the Earth is?
Around 4.5
4.5 what?
billion years.
4.5. Excellent. Excellent. Okay. And this has been estimated by the most accurate estimates have been made from dating of meteorites. If you look at radioactive dating of rocks, some of you geologists would be more familiar with it, that some of the oldest rocks are in the billion-year time scale as well. I've just written down a few over here. Augusta Gneiss in Northwest Canada, which is about 4.03 billion years old. Then you have rocks in Greenland, Western Australia, which are Swaziland, which are all close to it. So from the oldest rocks, you can put a lower limit to it, okay? That the Earth must be at least so many billion years old. The problem with the Earth is that the Earth has gone through various processes on the surface itself, which makes it unreliable to get a very accurate age. But you can at least show that it is greater than a certain age, which you infer from radioactive dating. You'd have heard a lot about carbon dating, but the lifetime is relatively small. You can see it's about 5,700 years or so. So you need elements with a larger lifetime to be able to date rocks or even meteorites. And uranium-238, I've written down over here, is about 4.47 billion years. So besides the Earth, one can also look at the earliest microbial colonies. And the earliest microbial colonies are also about, close to about 3.5 billion years. So as I said, the Earth's core mantle crust is constant mixing. Of plate tectonics, there's been weathering of the surface. Sometimes certain age gaps which are missing because of the effects of the evolution of the Earth's crust. There seems to be some 1.2 billion years of rock missing in the Grand Canyon. So as I mentioned that in terms of dating, meteorites would probably provide you the most reliable estimate of the solar system. We've also got lunar samples. Moon is not subject to the same dynamics as the Earth, but they keep getting bombarded, as you can see from the craters. Then meteorites, the early studies which were done was by Claire Patterson at Caltech, using sort of specimens from the Arizona crater and put it about 4.53 to 4.58 billion years. So this was work done in the 1950s itself. Today, we have many more samples of meteorites, and the oldest known meteoritic matter are those calcium aluminum rich inclusions which I spoke about, sub-millimeter to centimeter size, and these possibly condensed during cooling of the nebular material from which the solar system formed. So as I mentioned, that these effectively date the solar system, but you need material with long half-lives. The decay of uranium 238, 235, 232 thorium leads to stable radiogenic isotopes of lead, Pb. Radiogenic means the result from radioactive decay chains. Okay. And you also have a stable non-radiogenic, not radiogenic isotope of lead, which is 204. So over time, if you had, for example, measured the amount of 204 lead to the radiogenic ones, uranium or thorium would decay, and the ratios of this would keep increasing. So that is one sort of way of trying to determine the age. You could also use ratios. For example, 205 comes from uranium 235, 206 comes from uranium 238, and then you know the decay constants of lambda 1 and lambda 2, but you need a handle on the ratio of U35 to 238. This you measure and this you know to get a handle on the time. So these have been taken as average values. There's a bit of uncertainty in that, but in spite of that, the ages are quite reliable. I've not even written the third decimal place to which they quote the number of years. This is a relatively recent paper by Connolly et al. Published in Science, which from where I got this number, 4.57 billion years, which is what you all have said as well. And this actually paper was quite interesting in the sense that there were ideas about whether the inclusions and meteorites formed at similar times or later. And they showed that within the areas of measurement, they were very similar timescales that they formed. Now, the other interesting ways of actually people have tried to also understand meteorites is to look at cosmic ray tracks in meteoroids. So we have talked about cosmic rays and the tracks that they can cause. They may go right through a meteorite as well, but when they interact with it, they can leave tracks on it. And this is particularly true for those with heavier nuclei Z greater than 20. And one has also seen similar tracks in the helmets of astronauts. In fact, they have also deliberately tried to study these showers by trying to capture these in the helmets over here. And astronauts have also complained about seeing flashes of light, which is something I'm not sure is very well understood as yet, whether it is cosmic ray particles hitting the retina and exciting it, or whether it is directly hitting the brain cells and exciting it. I'm not too sure that it is very well understood, but that is something which also happens to astronauts when they're in outer space and exposed to these cosmic ray particles. But with suitable calibrations, you can also try and estimate ages from these, but obviously the dating processes gives you far more accurate estimates. Now, when cosmic ray particles hit meteorites, they can also break up of heavier elements into smaller ones, and these could lead to radiogenic elements whose ages can be determined. There could be spontaneous fission as well of very heavy nuclei. These can be distinguished from the kinds of tracks they leave. So these are also aspects which people look at, and they also give you a handle on how long meteorites may be traveling in space. So you can see it is not just the ones of radioactive dating, but also cosmic ray tracks. So these are physical processes which keep happening in interstellar space. So as you all mentioned, the age of the Earth is about 4.57 billion years. And compare this to the age of the Milky Way, which is about 13.5 billion years, and the age of the universe, which is 13.8 billion years. Now, as I mentioned earlier, that the ages of the rocks which have been determined is close to it. And one of the early estimates of the Hubble constant, which Hubble estimated, and the inverse of it gives you the age of the universe. Those days, the Hubble constant was far, far less accurately determined. They gave you age of rocks, age of the universe, which is smaller than the age of the rocks. So there was clearly a problem with the estimate of the Hubble constant at that time. But today we have a consistent picture. And you can see that the age of the Earth and the age of the Milky Way and the age of the universe. This is about less than half the value of the age of the galaxy and the age of the universe. In addition to the meteorites, dust is something which one has to also consider. Dust plays an important role in our study of the interstellar medium as well. But over here on the Earth, any small solid particle, rocky or icy, is referred to as dust. They are there in the interplanetary medium, surfaces of rocky planets, atmospheres of gaseous planets. Comets shed dust as they orbit the sun. We talked about the dust tail right in the beginning. Asteroids shed dust. They're present in planetary rings. They're present in interstellar medium regions of star formation in giant molecular clouds. They're present in the nuclear regions of active galaxies. So dust is a very important component of a universe, and it is important to study it. Cooling of dust, which gets heated up, we saw that it leads to copious amounts of infrared emission. And there have been attempts to study dust collected from the Earth's stratosphere. Then, as we learned, as we know, that lunar rock samples from the manned Apollo missions, unmanned missions could go even further. And even from unmanned missions, the Chinese mission, which was an unmanned mission, and even Russian missions, which were unmanned, picked up rock samples from the moon. And then you have had longer space missions to collect samples from comets as well as asteroids. The Stardust Mission in 1999 to 2006 collect dust samples from the coma of comet Wild 2, as well as cosmic dust. And these icy outer regions of these comets are not isolated. They suggest large-scale mixing. And there was a Japanese mission, Hayabusa, which actually landed on a small near-Earth asteroid named Itokawa. And this is followed by Hayabusa 2, which returned samples from another near-Earth asteroid in 2020. So these are aspects also which astronomers and space scientists gather to try and understand dust and rocks and see if they give any clues towards the origin of life itself. NASA's mission OSIRIS-REx, OSIRIS stands for Origin Spectral Interpretation Resource Identification Security Regolith Explorer. It landed in the near-Earth asteroid called Bennu. It collected samples of rocks and materials from the surface, and it is yet to return to Earth, which is expected in 2023. So these studies of these rocks are likely to give us additional clues towards understanding how planets may have formed, improve our understanding of asteroids. And if they have any material which we relate to life, it may also give us clues towards the origin of life. So you can see that material particles like asteroids also play a very important role in terms of our understanding of the universe.